Last but not least, we're going to work our final optimal portfolio case. This is case 4. This is probably the most relevant. Here we're working on finding an optimal portfolio of multiple risky assets. All right. So you can think of, you want to put together a portfolio of 5 or 10 or 15 stocks or funds to be well diversified. We're going to cover that here in this video and in a subsequent example. All right. Let's talk about this. So before we do anything, we're going to use matrix algebra to do this. I think this is going to be the easiest way. Let me just run a real quick refresher. All right, on matrix algebra. Suppose you have 3 equations, a 3-equation system here. 4x squared plus 2x minus 1, 2x squared plus 6x plus 4, 6x squared minus x plus 2. All right, if I were to put this in matrix notation, what I do is I just strip off the x squareds, the x's, and the constant. Does this make sense? And so I get a 3 by 3 matrix that has what I'll call the coefficients in front of those variables. Right? 4x plus 2x minus 1 is just going to be 4, 2, and negative 1 in the first row of this 3 by 3 matrix. 2, 6, and 4 is the second row, and 6, negative 1, and 2 is the third row, okay? So this is what a matrix looks like. The reason that I'm going to do this is because what I want to do is do some matrix multiplication, which is way easier to do when we're dealing with a whole bunch of different equations here, right? So recall, when I take the variance of the portfolio, I have to account for the covariances. I have to account for the covariances of each individual pair of stocks or assets in the portfolio. That's going to be a nightmare. So what I'm going to do is I'm going to use matrix notation. A vector is an n by 1 or a 1 by n matrix. All right. So let this vector v1, it's underlined. That's how I'm going to denote matrices or vectors, is 2, 5, and 1. So this is an n by 1, a 3 by 1 matrix. Let V2 have the following form, 5, 1, and 7. Again, this is an n by 1 matrix. Now I can multiply these vectors to get a single solution by doing the following. What I'm going to do is I'm going to transpose vector 1. Notice that little slash right there. That means I've transposed it. And look at what I've done. So I've taken the n by 1 vector and I've made it a 1 by n vector. So I've turned it on its side. So instead of having 2 in row 1, 5 in row 2, and 1 in row 3, I've now transposed that where I now have 3 columns and just 1 row. Now I can multiply the transposed v1 vector by the v2 vector, all right? So a 1 by n vector multiplied by an n by 1 vector will give me a 1 by 1 solution. How do I do this? I take this v1 transposed vector and I take 2 times 5 plus 5 times 1 plus 1 times 7, and that will give me a solution of 22. All right? So this should just be a refresher of matrix algebra. Some of you may have never seen this before. That's all right. We'll work some problems. We'll work an example here that will help you in the next video. But what I'm going to do here to find the optimal portfolio of multiple risky assets is I'm going to do something very simple. I'm going to have to use a program. I'll use Excel to do this. I'm going to find the expected return of the portfolio, which is the weight vector. Again, the weights are each individual weight that I'll put on each individual asset in the portfolio. I'm going to transpose that weight vector and multiply it by a return vector. The weight vector is an n by 1 weight vector, so it consists of all of the weights that I'll have for each of the assets. The return vector is also an n by 1 vector that has the returns for all of the assets that I'm going to put in my portfolio. I'm going to take that weight vector and transpose it, so now I have a 1 by n vector multiplied by an n by 1 vector, and I'm going to get a 1 by 1 solution. That's going to be the expected return of the portfolio. Likewise, calculating the standard deviation of the portfolio, I'm going to use the standard deviation instead of the variance here just for simplicity. What I'm going to do is I'm going to take the square root of the weight vector transpose, so that's now going to be, once it's transposed, a 1 by n vector, times an n by n matrix called the variance covariance matrix. So this is going to account for all of the variances of each of the individual assets in my portfolio, as well as all of the covariances of all of the individual pairs of assets in my portfolio. So this is an n by n matrix, variance covariance matrix. And again, I'm going to multiply this again by the weight vector, which is a n by 1 vector. So I've transposed the weight vector here, so I have a 1 by n weight vector that's been transposed times an n by n. So the product of these two matrices is going to give me a 1 by n. 1 by n times n by n is going to give me a 1 by n. And then I'm going to multiply that again by an n by 1 to get a 1 by 1 solution. I take the square root of that solution and I get the standard deviation of the portfolio. Simple enough. I'm going to maximize the ratio of the expected return of the portfolio to the standard deviation of the portfolio subject to the weights summing to 1. That is all of the weight vectors summing to 1. Okay? The weight vector summing to 1. Does that make sense? So I'm going to maximize this objective function subject to this constraint using Excel. I'm going to do all the matrix multiplication in Excel, and we're going to come up with a model that would allow us to find the optimal weights for a whole bunch of different assets that we want to put into our portfolio.